What if I told you that the greatest military machine in human history operated without electricity, microchips, or satellite navigation, yet was more reliable than any modern drone? We are accustomed to thinking that modern combat robots packed with electronics represent the pinnacle of weapons evolution, but history proves otherwise. Ancient Rome created an engineering ecosystem that allowed it to wipe cities off the face of the earth and break the will of entire nations using only wood, animal sinews, and mathematics. Their artillery did not depend on supplies of rare batteries, was not afraid of electronic warfare, and worked in any mud where modern technology would have turned into useless scrap metal. It was a triumph of mechanics, standardization, and cruel genius that turned war into an exact science thousands of years before the advent of the first computers. Watch the video to the end to find out how Roman engineers solved the black box problem and why their assembly techniques are still the envy of space rocket designers. What if I told you that everything you believed about the artisanal production of antiquity is not true? The Roman war machine was not based on the brute force of slaves, but on a unique mathematical code that made their artillery universal anywhere in the known world. Every engineer, from foggy Albion to hot Syria, knew by heart the formula that turned the chaos of construction into perfect order. The main secret was not the shape of the machine, but the diameter of the hole in the frame through which elastic bundles of tendons were passed. It was this diameter, calculated according to the weight of the stone or the length of the arrow, that dictated the dimensions of all other parts of the structure without exception. This meant that the Romans did not need drawings in the modern sense of the word, as everything was scaled from a single number. If you knew the weight of the projectile, you automatically knew the thickness of the beams, the length of the levers, and the size of the trigger mechanism simply by multiplying the base module by the necessary coefficients. This system made it possible to produce spare parts at one end of the empire and fit them perfectly onto machines assembled at the other end, 1,000 kilometers away. It was the first system of complete industrial standardization in human history, appearing long before Henry Ford and his assembly line. Imagine a level of logistics where the army does not carry spare machines with it, but only metal components and the knowledge of its engineers. Wooden parts could be made on site from any suitable forest because the proportions were universal and known to every craftsman. This made Roman artillery practically immortal. As long as the engineer was alive and there was wood, the machine could be reborn again and again. Modern robots die without factory spare parts, but a Roman ballista could be repaired by a simple legionnaire with an axe and knowledge of proportions. The accuracy of this mathematical model was such that machines of different sizes had absolutely identical ballistic characteristics if they were built according to the formula. This allowed gunners not to retrain when switching from a light Scorpion to a heavy ballista, as the principles of aiming remained unchanged. This standardization saved years of personnel training and made the Roman army a unified, coordinated organism. In a world where every city had its own measures of length and weight, the Roman army spoke the common language of engineering mathematics. This system eliminated the possibility of errors during assembly, as each part was checked by a simple ratio to the main module of the whole. An engineer could not make a mistake in the length of the frame, because it had to be exactly a certain number of diameters, and not a centimeter more. This created an incredible margin of safety, as the formula was derived empirically, taking into account enormous loads. The Romans did not simply build weapons. They built a mathematically sound guarantee of the enemy's destruction. Compare this to modern technology, where the failure of a single unique chip renders a multi-million-dollar tank useless. The Roman system was resistant to the chaos of war because its complexity lay in its design, not in its materials. They understood that on the battlefield, it is not the one with the most complex device who wins, but the one who can repair their weapons faster than the enemy. And this principle of the golden module became the foundation of their millennial domination on the battlefields of Europe and Asia. This is the fundamental difference between the Roman approach and the modern one. We depend on supply chains, while they depended only on knowledge. Knowledge of the formula was the most closely guarded secret, passed down within the caste of military engineers as sacred knowledge. Whoever possessed the formula possessed the power to destroy city walls with Swiss watch precision. And this formula worked flawlessly, century after century, without requiring firmware updates or battery replacements. Be sure to subscribe to our channel right now so you don't miss the next analysis of forgotten, ancient technologies that surpass modern ones. We are very interested in hearing your point of view. What do you think about such a standardization system in the ancient world? Write about it in the comments. Want to know a secret that will change your understanding of energy? Roman machines did not use gunpowder or steam, but they generated tremendous kinetic energy capable of piercing shields and armor. At the heart of each throwing machine was a torsion spring, a tightly twisted bundle of elastic fibers that worked with incredible efficiency. It was a biological energy accumulator that stored the strength of several people and released it in a fraction of a second. The Romans used not just ropes as material for torsion springs, but specially treated animal tendons, mainly the neck tendons of bulls. This material had unique elasticity and strength, allowing it to be twisted to critical values without breaking. The process of preparing the tendons was complex and laborious, requiring thorough cleaning, drying, and oiling of each fiber. But the result was a spring that knew no fatigue and could work for years with proper care. There is a common myth that women's hair was used in critical situations, and this is partly true, as confirmed by historical chronicles. Human hair has high tensile strength and elasticity, which made it an acceptable substitute for strands during a siege when resources were depleted. The women of Carthage and Rome did indeed sacrifice their braids to enable the city's defenders to fire a few more shots at the enemy. This adds a dramatic touch of sacrifice to the engineering history behind each shot. The secret to its power lay in the pre-tensioning of the bundles, which was achieved using special levers and ratchet mechanisms. Engineers tensioned the torsion springs to such a degree that the sound of striking them resembled a musical instrument, and it was by the sound that they determined the uniformity of the tension. If the springs on the left and right side sounded at different pitches, it meant there was a skew that would lead to a miss. Tuning a ballista was like tuning a giant, deadly harp, where a false note could cost a life. Torsion machines had a much higher efficiency compared to simple bows or crossbows that used the energy of the bending of the arms. The twisting energy allowed the arms of the machine to be short and rigid, which ensured a compact design with enormous power. The stone or arrow was accelerated throughout the entire movement of the lever, reaching speeds invisible to the eye. The impact of such a projectile was terrifying. Heavy spear bolts pierced 2 or 3 people standing one behind the other. However, these engines were capricious and required constant protection from moisture, which was the main enemy of the torsion bars. Roman artillerymen carried oiled leather covers with them to cover the torsion bars at the first sign of rain or fog. A wet cable instantly lost its elasticity, turning a formidable machine into a useless pile of firewood. This required high discipline and constant maintenance, which was the hallmark of the Roman army. Unlike modern hydraulic or electric drives, torsion bars could not freeze or shut down due to a software failure. Their condition was always obvious. A visual inspection and sound check gave a complete picture of combat readiness. The simplicity of diagnostics allowed problems to be eliminated before the battle began, rather than in the heat of battle. It was honest mechanics, where strength depended on the quality of the material and the skill of the adjustment. The elasticity of the torsion bar also depended on the air temperature, and experienced engineers made adjustments for frost or heat. In winter, the wires became stiffer and could break, so their tension was slightly loosened before firing. In summer, on the contrary, additional tightening of the levers was required to maintain the firing range. It was a living weapon that breathed in unison with nature and demanded respect. Compare this to modern drone batteries, which lose their charge in minutes in the cold and shut down. The Roman torsion weapon worked in the snows of Germany and in the sands of Parthia if it was cared for by skilled hands. This technology was the pinnacle of biomechanics, using the natural properties of organic matter to create superhuman strength. Did you know that the sound of Roman artillery in action was one of the main factors in exerting psychological pressure on the enemy? In the next chapter, you will learn about sniper weapons that were banned because of their inherent cruelty. What I am about to show you is banned in 12 countries under the modern understanding of the humanity of war, but for Rome, it was the norm. We are talking about the Scorpion, a light crossbow machine that became the forerunner of all sniper rifles in the world. It was not a weapon of mass destruction, but one of precision elimination, designed to shoot enemy commanders and standard bearers. Its accuracy was so phenomenal that from a distance of 300 meters, an experienced crew could hit a running man in the head. The Scorpion differed from its larger counterparts in its elegant design and incredible reloading speed. One person could aim it by turning simple mechanisms, while another loaded the arrow and drew the bowstring. This created a density of fire comparable to that of a modern machine gun crew, only instead of bullets, heavy bolts with iron tips flew. These bolts were capable of piercing any shield of that time and nailing its owner to a tree or the ground. The uniqueness of the Scorpion lay in its low trajectory, which made the shot almost straight. The enemy did not hear the whistle of the arrow falling from above. He simply saw his comrade suddenly fall with a pierced chest. This caused panic in the enemy's ranks, as death came instantly and inevitably without warning. On the fields of Gaul and Britain, the Scorpions mowed down barbarian leaders before they could even give the order to attack. The design of the Scorpion was so successful that it remained virtually unchanged throughout the centuries of the empire's existence. When forming a battle line, the legion would place 60 such machines in the gaps between the cohorts, creating a continuous zone of death in front of the front line. Any attempt to approach the Roman formation was met with a barrage of armor-piercing projectiles that did not bounce off the armor. This allowed the legionaries to engage in hand-to-hand combat with a demoralized and depleted enemy. Interestingly, each bolt for the Scorpion had a special feathering cut from wood or leather to stabilize its rotation. These were not just enlarged arrows for a bow, but aerodynamically perfect projectiles designed for long-range flight. Master armorers achieved perfect balance so that the projectile's center of gravity provided maximum penetrating power on impact. A hit from such a bolt was guaranteed to tear off a limb or crush bone into fine powder. Roman engineers equipped the Scorpions with sighting devices that allowed them to fire with lead. They understood how the target moved and marked the frame for quick fire correction on moving horsemen. It was a prototype of a collimator sight implemented using simple mechanical solutions. Training to fire a Scorpion took months, and the operators of these machines were considered the elite of the legion. The psychological effect was enhanced by the fact that the Scorpion itself was inconspicuous against the backdrop of massive ballistas and siege towers. It was a silent killer that hid in the shadows and struck with surgical precision. Often the enemy did not even understand where the fire was coming from until they had lost half of their officers. This threw the barbarians, who were accustomed to fair face-to-face combat, into chaos. Modern sniper systems require sophisticated optics, laser rangefinders, and ballistic calculators. The Roman Scorpion achieved similar tactical results thanks to the experience of the gunner and the perfection of its mechanics. It was not affected by lens glare and was not afraid of shocks, continuing to work even after falling from a cart. This machine proved that size does not always matter in artillery and that accuracy is more important than brute force. Lightweight, maneuverable, and deadly, the Scorpion became the ideal tool for controlling the battlefield. Don't forget to like this video if you were impressed by the engineering genius of the ancient Romans. Don't forget to subscribe to the channel so you don't miss any new videos. Are you ready for the shocking truth about how the Romans demolished stone fortifications without explosives? Meet the onager, a machine named after a wild donkey for its untamed temper and monstrous recoil when fired. If the Scorpion was the sniper, the onager was the Roman army's sledgehammer, designed to destroy stone and flesh. It was a single-shouldered torsion catapult capable of hurling huge boulders hundreds of meters. The onager worked on the principle of a sling attached to a powerful lever, which was set in motion by a giant horizontal torsion bar. When fired, the lever described an arc and struck the stop cushion with force, ejecting the projectile from the sling. This impact was so strong that the machine literally jumped up and down on the spot, kicking the ground with the rear part of the frame. It was because of this kicking that soldiers gave it the nickname of a wild animal that cannot be tamed. The projectiles for the onager were not only processed stone balls, but also pots with incendiary mixtures or even animal carcasses to spread disease. It was a weapon of terror that not only destroyed walls, but also burned cities, spreading plague and panic among the besieged. A single large stone from an onager hitting a dense formation of infantry would turn a dozen people into a bloody mess. The sound of a flying stone was like thunder, forcing the defenders of the walls to press themselves into cover. To operate one large onager, a crew of 8 to 10 men was required to pull the lever with the help of a winch. It was hard physical work that required coordinated action to prevent the mechanism from breaking down and injuring the artillerymen themselves. Safety when working with the onager was relative. The lever could kill a distracted soldier instantly. But the Romans took this risk for the destructive power that this machine provided. Onagers were usually built directly at the site of the siege, as it was practically impossible to transport such a huge machine in assembled form. Engineers carried only metal parts and torsion bars with them, and the wooden frame was cut from nearby forests. This made the onager an incredibly adaptable weapon. Its size depended on the availability of trees and tactical necessity. If a powerful tower needed to be destroyed, a giant monster was built. If it was just necessary to terrorize the infantry, smaller versions were assembled. An interesting feature was the trajectory of the projectile. It was high and curved, allowing stones to be thrown over walls. This meant that no building inside the besieged city was safe. The Romans methodically destroyed houses, temples, and warehouses, forcing the garrison to surrender not by storming the city, but by exhaustion and constant fear of death from the sky. The vibration from the operation of the onager battery was such that it could shake the masonry of its own fortifications if they were placed on the walls. Therefore, special platforms were prepared for them, from compacted earth or wooden decking to dampen the recoil. Engineers carefully chose positions so that the machines would not destroy themselves in the process of firing. This required a deep understanding of physics and the properties of materials. The onager was a symbol of the inevitability of Roman retribution. It could strike a single point for days until the wall collapsed. Modern robots are often limited by their ammunition, but the onager could fire anything lying at its feet, from stones to building debris. This made its ammunition virtually endless as long as there was solid matter around. This machine was not known for its sniper-like accuracy, but it didn't need it. It relied on mass and energy. The wild temperament of the onager was subjugated by the iron discipline of the legion, creating a destructive tandem of chaos and order. Which modern machine do you think can compare to the onager in terms of psychological effect? In the next chapter, you will learn how the Romans calculated the trajectory of a shot without computers or calculators, and why their methods worked flawlessly. Roman engineers did not have digital displays, but they had a deep intuitive understanding of the physics of flight. They had spent years observing the behavior of stones and arrows in the air and knew how slightly tighter strings changed the trajectory. Aiming was accomplished using a complex system that included sights, plumb lines, and graduated scales on the frame of the machine. These markings allowed the elevation angle and direction to be maintained even when the machine was standing on uneven ground. The main tool of the gunner, called a librator, was his experience and the correction table he kept in his head. Roman military schools specifically trained such people, forcing them to repeat dozens of situations until they began to feel the behavior of the machine almost instinctively. Each turn of the tension screw or change in the elevation angle of the frame changed the flight range by a strictly defined number of steps. This data was not recorded in writing, but was passed down from master to apprentice, becoming part of the military craft. The liberator gradually accumulated personal experience related to a specific machine, as each ballista had its own character. He understood how much the torsion bars could be overtensioned to achieve the desired force without damaging the mechanism. He kept the exact values of the steps in his memory and quickly compared them with the conditions on the battlefield. This made Roman artillery both simple and effective. The sighting process began with a test shot, which was called a sighting stone. Such a stone was usually of medium weight so that the reaction of the machine would be predictable and would not overload the structure unnecessarily. Special observers monitored the point of impact and transmitted signals to the gunner using flags or gestures. The observers were positioned on heights or towers so that they could see distant areas of the field. The librator instantly recalculated the data and understood how many steps the shortfall or overshoot needed to be changed. It was a live feedback loop that worked no worse than modern fire control systems. If the stone fell too close, the librator increased the tension of the torsion bars or changed the angle to give the projectile more energy. If the stone veered off course, he adjusted the side guides that kept the chute level. Such minor adjustments could make the difference between hitting a wall and striking the desired section of the fortification. Sometimes observers shouted out the distance if the enemy was nearby, and there was no time to wait for a signal. Everything happened quickly and without unnecessary movements, because every second counted on the battlefield. Thus, sighting became a refined process. To fire at invisible targets hidden behind walls or hills, they used simple trigonometry and instruments similar to modern theodolites. These instruments were wooden frames with a stretched string that allowed them to measure angles relative to the horizon. The Romans were able to determine the height of an obstacle by its apparent angle and the distance to it without approaching the enemy. Knowing the distance and weight of the stone, the engineers set the angle of the ballista's chute to achieve the desired arc. This method allowed them to hit targets that seemed unreachable by direct fire. It was mathematics applied to killing, devoid of magic or divination. Engineers often surveyed the terrain in advance if they knew their army would be laying siege. They did this at dawn, when the light was even and shadows did not distort the shapes of the hills. Using their simple instruments, they constructed a rough map in their minds, marking heights, ravines, and possible enemy hiding places. These notes were not written down, but kept in memory so that the correct angle could be quickly set at the right moment. This approach required attentiveness and the ability to work with numbers, but the Romans coped well with this. Thanks to this, their artillery did not fire at random, but at calculated points. An important factor was the standardization of the weight of the projectiles. Stone cores were hewn by stone cutters to a perfect spherical shape and checked with calibration rings. For this purpose, smooth bronze rings were used, which did not change shape over time. If a cannonball did not fit through the ring, it was rejected, as it could get stuck or fly unpredictably. If the cannonball was too small, the energy of the shot was lost, and the trajectory became shorter than calculated. Standardized cores were trusted because they provided the same air resistance. This obsessive concern for ammunition standards ensured trajectory stability from shot to shot. Stonecutters worked near the camp to quickly replenish shell supplies during long sieges. Their work was hard, as they had to shape the stone into an almost perfect sphere by hand. But it was their work that allowed the artillerymen to be confident in the behavior of each shell in flight. Often, dozens of such craftsmen worked in one camp, ensuring a continuous flow of ammunition. Commanders valued this craft, understanding that the speed of breaching a wall depended on the quality of the cannonballs. Therefore, the craftsmen were provided with tools and protected from overwork so that they would not compromise quality. Gunners even took into account the wind, which could significantly blow off the scorpion's feathered arrow or change the flight range of a light stone. They threw a handful of dust or grass into the air before firing to assess the strength and direction of the wind. Sometimes they simply raised their hands and felt the movement of the air with their skin if the wind changed too quickly. These adjustments were made on the fly, based on muscle memory and thousands of hours of training at the firing range. Roman camps always had special areas where gunners practiced shooting. This experience gave them confidence even in the most difficult conditions. Sometimes the wind changed right in the middle of battle, and the librator had to make a decision in a split second. He looked at the smoke from the fires or at the banners to understand where the wind was blowing. This allowed him to quickly change the angle or tension without stopping the firing. Windy weather was considered a test for every gunner, and only the most experienced could cope with it without noticeable errors. But even such conditions did not paralyze the Roman artillery, as each shot was accompanied by constant adjustments. This made the system flexible and stable. The Roman aiming system was stress-resistant. It had no fragile lenses that could break or batteries that could run out. The scales were carved directly into the wood or cast in bronze. They were eternal and indelible. The Romans sought to make their equipment durable so that it could withstand long campaigns and changes in climate. Even if the gunner died, his assistant could take his place, as the marking system was uniform throughout the army. Thanks to this, any new soldier could quickly figure out how to use the machine. Such unification made it possible to maintain combat readiness even after heavy battles. Even in rain and mud, the control system remained accurate because the markings remained visible and understandable. The bronze elements did not rust, and the wood was treated with oil to protect it from moisture. The machines could stand in the open air for weeks and still remain operational. This was especially important in campaigns where artillery had to be dragged across wet or mountainous terrain. It is noteworthy that the Romans thought through such situations in advance and made the machines as easy to maintain as possible. All this made their artillery reliable and durable. Interestingly, the Romans used pre-calibrated sights for night firing. During the day, they fixed the position of the machine with wedges and stops, aiming at a gate or crossroads. Then they marked small lines on the ground indicating the direction and angle of the barrel. At night, they could fire blindly, simply loading and firing the mechanism, knowing that the projectile would fly straight to the target. This method allowed them to create the illusion of continuous pressure on the enemy. This created the effect of the omnipresence of Roman artillery, which never slept. In the dark, the Romans also used torches to see the loading area, but they did not illuminate the target itself so as not to reveal their position. The silence was broken only by the tension of the strings and the dull thud of the mechanism, which put strong psychological pressure on the enemy. Many opponents believed that the Romans were firing in complete darkness, although everything depended on pre-prepared landmarks. Such deceptive impressions reinforced the fear of Roman technology, and the longer the siege lasted, the more the nighttime bombardments wore down the defenders' morale. This is what made nighttime operations an important part of Roman strategy. Surprisingly, their methods of calculation without the use of zero and decimal fractions yielded results sufficient to conquer the world. The Romans used simple numbers and ratios that were understandable even to those who did not know how to calculate in depth. This analog computer ran on porridge and wine, but solved ballistic problems with frightening efficiency. Their calculations were based on observation, practice, and repetition, which made them extremely reliable. Even without complex mathematics, the Romans confidently hit targets at considerable distances, and this practicality became one of the reasons for their military success. What if I told you that I discovered this by accident while studying reports on modern military conflicts? The main problem with modern technology is logistics and maintenance. The Roman siege engine was ingenious in that it was completely repairable in the field using local resources. If a modern robot's servo motor breaks down, it has to be sent to the factory. If a ballista's lever broke, the legionaries would go to the nearest grove, chop down an oak tree, and carve a new one. This concept of repairing from the ground up made the Roman army autonomous to a degree unattainable by modern troops. They did not need high-tech workshops with clean rooms. A forge and a carpenter's workbench solved 99% of their problems. Metal parts, fittings, washers, trigger hooks, were made of durable iron and could outlive the wooden frame itself several times over. They were simply transferred from the broken machine to the new one. The standardization we mentioned earlier played a key role here. Every blacksmith in the legion knew the dimensions of standard parts. There was no need to wait for an order from Rome. Spare parts were forged right in the camp between battles. This ensured the continuity of combat operations as equipment downtime was minimized. The army repaired itself, supplied itself, and reproduced itself. The wood used for the machines was also carefully selected. Oak for the power frames, ash or elm for the elastic levers. Engineers knew the properties of trees in every region where the legion invaded. They were not just mechanics, but also botanists, able to find the right material in unfamiliar forests in Germany or Africa. This knowledge of the environment made them independent of long supply lines. Unlike plastic and composites, wood and iron warn of breakage. Wood begins to crack, metal bends, wires fray. A mechanic could see and hear the problem long before it became critical. Modern electronics die silently and suddenly, leaving the operator with nothing. Roman technology provided an opportunity for preventive maintenance. The simplicity of the design meant that there were a minimum number of moving parts in the machine. The fewer parts, the less likely a breakdown. This is the golden rule of engineering, elevated to an absolute by the Romans. There was nothing to short-circuit, oxidize, or lose contact. Only the rough, understandable physics of levers and tension. The durability of the machines was enhanced by their modularity. A ballista could be disassembled for transport by mules along mountain trails and reassembled in a couple of hours. This made it possible to deliver heavy artillery to places where modern tanks or trucks simply could not go. The Romans carried their robots through swamps and mountain passes, literally on their shoulders. Even a machine damaged in battle often continued to fire, albeit with less efficiency. A broken piece of the frame or a crack in the base did not completely disable it. This quality of combat resilience allowed battles to be completed even with half-destroyed equipment. A modern drone with a damaged propeller falls. A Roman onager with a crack fires 10 more shots. This philosophy of rough reliability allowed Rome to wage wars of attrition for years. They were not afraid of equipment wear and tear because equipment was part of the cycle of nature. Forests grew everywhere, iron was mined, and veins were taken from livestock. Do you think such maintainability is an advantage in modern warfare? Or is high technology worth the risk of breakdown? In the next chapter, we will discuss monsters that moved on their own, inspiring terror with their mere appearance. When the Romans wanted not only to destroy a wall, but also to crush the will of the defenders with their grandeur, they built siege towers called helipoli. These structures were true ancient skyscrapers on wheels, sometimes reaching the height of a 3-story building or even higher. The higher the tower, the more archers and throwing machines could be placed on its levels. Inside such a structure were legionnaires, engineers, and artillerymen who worked in unison, as if they were inside a warship. Each floor housed scorpions and light ballistas, creating dense fire across the entire line of defense. In essence, it was a moving multi-story tank from which heavy fire was directed from top to bottom. These towers made a strong psychological impression, as their appearance meant that the enemy could no longer take refuge behind the height of the wall. Their slow movement looked like the approach of a huge structure that could not be stopped by conventional means. Even if the defenders tried to set fire to the tower, the Romans had many ways to save it from the flames. Therefore, the siege tower itself became a symbol of Roman relentlessness and military discipline. It showed that the empire was not just going on the offensive, but intended to bring the siege to an end. This pressure broke the morale of the defenders even before the actual assault began. The towers were covered with raw hides or metal sheets to protect them from flaming arrows. The raw hides not only did not ignite, but also emitted steam, which prevented the fire from spreading. Inside were tanks of water and vinegar for extinguishing fires, which made the tower a self-sufficient survival system under siege conditions. This colossus was moved by mechanisms hidden inside in the efforts of hundreds of people or oxen, safely sheltered behind the hull. Animals and people pulled the tower slowly but steadily, while engineers controlled its direction. To the enemy, it looked as if the mountain itself was slowly and inexorably advancing on their city. From the upper floors of the tower, Roman archers had a decisive advantage. They fired at the defenders of the walls from above, depriving them of cover behind the battlements. Thanks to their height, they could see all the enemy's movements and could suppress even those who tried to hide behind towers and wall projections. At the same time, a special folding bridge known as a corvus allowed the legionaries to quickly cross the wall in a single stream. This made it possible to avoid the dangerous climb-up ladders, which the defenders often threw down. As soon as the bridge was lowered, Roman soldiers stormed the wall, acting in a compact and organized manner. Thus, the assault turned from a risky attack into a methodical clearing of the fortifications. Engineers carefully calculated the weight and center of gravity of the tower so that it would not tip over when climbing the rampart or moving over uneven ground. To do this, they used internal ballast weights, which were positioned so that the entire structure remained stable, even under the impact of stones and arrows. If the terrain was particularly difficult, the Romans reinforced the tower with additional support beams. Such measures allowed them to conduct assaults in conditions where other armies would simply not dare to use such machines. Engineering training made the Roman army predictably dangerous. Therefore, the tower itself showed how seriously the Romans approached each siege. Siege towers were not just a means of transport, but an engineering marvel. They had a wheelbase with a primitive, independent suspension, which helped to compensate for uneven ground and keep the tower upright. The road in front of the tower was leveled by special sapper units, often working under enemy fire, creating an almost flat surface for it. In some areas, they even added extra soil or stones to ensure smooth movement. As a result, a single tower could decide the outcome of a months-long siege in a single day if it was possible to bring it close to the wall. That is why helipoles were considered one of the most formidable tools of Roman siege warfare. If you think that automatic weapons appeared in the 19th century, you are mistaken. The Romans knew and used the polybolus, an automatic ballista capable of continuous fire. Invented by the Greeks and improved by the Romans, this machine had a magazine feed for arrows and a chain-driven cocking mechanism. By turning the crank, the operator simultaneously pulled the bowstring, fed a new arrow from the gravity magazine, and fired. The polyball did not require separate actions for reloading, which allowed it to achieve an incredible rate of fire for its time. While a conventional scorpion fired one shot, the polyball fired 3 or 4 arrows. This created a density of fire capable of stopping an infantry attack in a narrow passage or on a bridge. Mechanical feeding eliminated the human factor of error when loading in the heat of battle. The gear wheels and chain transmission used in the polybus were the pinnacle of precision mechanics in antiquity. It was a complex, expensive, and temperamental machine that was not used often, but where it appeared, the effect was stunning. The enemy simply could not understand how the Romans could fire continuously without lowering their arms. It was technological superiority in its purest form. The weak point of the polybolus was its complexity and sensitivity to dirt, so it was mainly used in garrison defense or on ships. However, the very fact that such a machine existed proves that Roman engineers came close to creating a machine gun. All they needed was gunpowder to complete the cycle. The effectiveness of siege engines was measured not only in kilojoules, but also in kilograms of fear. The sound of a heavy ballista's torsion bar being released resembled the sharp crack of a giant whip, which could be heard for miles. This sound was followed by the whistle of a flying projectile and the monstrous roar of an impact on stone or wood. This acoustic cannonade kept the besieged awake, exhausting their nervous systems around the clock. The Romans understood the psychology of war perfectly and used artillery to demonstratively destroy iconic buildings. Demolishing a statue of a local deity or destroying a ruler's palace was more important than killing 100 soldiers. It showed the powerlessness of local gods in the face of Roman engineering. Morale fell faster than walls collapsed. The whistling of stones flying from onagers was often amplified by drilling holes in them. Such a singing stone howled in flight like a banshee, striking superstitious terror into the barbarians. They believed that the Romans controlled evil spirits. It was a primitive but effective method of sonic warfare. The sight of a man torn in half by a ballistic bolt had a much stronger effect on the psyche of the survivors than a normal sword wound. It was a death that could not be defended against by fencing skills or bravery. The realization of their own helplessness in the face of the machine broke their will to resist. The Romans won battles in the minds of their enemies even before they entered the city. Roman siege engines became a thing of the past not because they became ineffective, but because the social structure that supported them disappeared. With the fall of Rome, the formula for standardization, the secrets of wire processing, and the mathematical school of liberators were lost. The Middle Ages reverted to simpler and less effective counterweight designs, trebuchets, because it lost the technology of precision torsion mechanics. We admire these machines today because they represent the perfect balance between complexity of design and simplicity of execution. This is a lesson for modern engineering. The best solution is not always the most high-tech one, but the one that works in all conditions. The Roman ballista was the Kalashnikov assault rifle of its time, simple, reliable, and deadly. Studying their blueprints, we see that many components of modern cranes, winches, and gearboxes have their roots in Roman military mechanics. They invented bearings, cardan transmissions, and ratchets long before the Industrial Revolution. We stand on the shoulders of giants who wore sandals and tunics. Roman machines proved that human intelligence can overcome any material limitations. Without high-quality steel and plastic, they created weapons that conquered the world. This reminds us that technology is just a tool, and that real power lies in a systematic approach and knowledge. We have seen that Roman siege engines were not just piles of wood, but the pinnacle of engineering thought, combining mathematics, biology, and psychology. They surpassed their modern counterparts in autonomy, maintainability, and the ability to operate in conditions of complete chaos. They were ideal soldiers. They did not require food, knew no fear, and obeyed the universal laws of physics. The history of Roman artillery is a textbook on efficiency, written in blood and sawdust. Which Roman machine did you find most impressive in terms of its engineering design? Was it the sniper Scorpion or the devastating Onager? Write your opinion in the comments and don't forget to subscribe to the channel to continue exploring the technologies of the past with us.